Hello, dear students, welcome to massive open online course on SWAYAM in chemistry. Myself, Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya No. 1, Air Force Station, Hindon. Dear students, in the previous module, you have studied about polarity of bonds, VSEPR theory, valence bond theory and hybridization. Dear students, after going through this module, you will be able to understand the following: orbital theory, linear combination of atomic orbitals, that is LCAO, bond order and its calculation, stability and magnetic character of molecule, comparing stability of various molecules and ions, molecular orbital theory of homonuclear diatomic molecules, hydrogen bonding. First of all, molecular orbital theory. Molecular orbital, that is MO, this theory was developed by F. Hun and R. S. Mulliken in 1932. The salient features of this theory are: the electrons in a molecule are present in the various molecular orbitals as the electrons of the atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry, they combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei depending upon the number of the atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. The number of the molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is called antibonding molecular orbital. The bonding molecular orbital has lower energy and hence greater stability than the corresponding antibonding molecular orbital. Just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. The molecular orbitals, like atomic orbitals, are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. Formation of molecular orbitals, linear combination of atomic orbitals, that is LCAO. According to wave mechanics, the atomic orbitals can be expressed by wave functions psi, which represent the amplitude of the electron waves. These are obtained from the solution of Schrödinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals, which are one electron wave functions for molecules, are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbitals has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in 1s orbital. The atomic orbitals of these atoms may be represented by the wave functions psi A and psi B. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals, as shown below. Psi molecular orbital is equals to psi A plus psi B, where psi A and psi B are atomic orbitals of atom A and B respectively. Therefore, the two molecular orbitals sigma and sigma star, that is sigma antibonding, this star depicts the antibonding, are formed as sigma equals to psi A plus psi B. Sigma bonding orbitals are formed by constructive overlap between atomic orbitals. Sigma antibonding is equals to psi A minus psi B. Sigma antibonding orbitals are formed by destructive overlap between atomic orbitals. Therefore, the molecular orbital sigma formed by the addition of atomic orbital is called the bonding molecular orbital, while the molecular orbital sigma antibonding formed by the subtraction of the atomic orbital is called antibonding molecular orbital as depicted in the figure. Formation of bonding, that is sigma, and antibonding, that is sigma star, represented by molecular orbitals by the linear combination of atomic orbitals psi A and psi B, centered on two atoms A and B respectively. Now, you can see in the figure the psi A and psi B and the atomic orbitals and their overlapping. Qualitatively, the formation of the molecular orbitals can be understood in the terms of the constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to constructive interference, while in the formation of antibonding molecular orbital, the electron waves, they cancel each other due to destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of the bonded atoms, because of which the repulsion between the nuclei is very less. While in case of an antibonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is a nodal plane on which the electron density is 0 between the nuclei, and hence the repulsion between the nuclei is high. Electrons placed in a bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. Therefore, a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. In contrast, the electron placed in the antibonding molecular orbital destabilizes the molecule. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. It may be noted that the energy of the antibonding orbital is raised above the energy of the parent atomic orbital that have combined, and the energy of the bonding orbitals has been lowered than the parent orbitals. The total energy of the two molecular orbitals, however, remains the same as that of the two original atomic orbitals. The condition for the combination of the atomic orbitals, the first is the linear combination of atomic orbitals to form the molecular orbitals takes place only if the following conditions are satisfied. The combining atomic orbitals must have the same or nearly the same energy. This means that 1s orbital can combine with another 1s orbital, but not with the 2s orbital, because the energy of the 2s orbital is appreciably higher than that of the 1s orbital. This is not true if the atoms are very different. The second rule is the combining atomic orbitals must have the same symmetry about the molecular axis. By convention, z-axis is taken as the molecular axis. It is important to note that atomic orbitals having same or nearly the same energy will not combine if they do not have same symmetry. For example, 2pz orbital of one atom can combine with 2pz orbital of the other atom, but not with the 2px or 2py orbitals because of their different symmetries. Third, the combining atomic orbitals must overlap to the maximum extent. Greater is the extent of overlap, the greater will be the electron density between the nuclei of a molecular orbital. Types of molecular orbitals. The molecular orbitals of the diatomic molecules are designated as sigma, pi and delta, etc. In this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. For example, the linear combination of 1s orbitals centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of the sigma type and are designated as sigma 1s and sigma antibonding 1s. The figure will show you if internuclear axis is taken to be in the z direction, it can be seen that a linear combination of 2pz orbitals of the two atoms also produces two sigma molecular orbitals designated as sigma 2pz and sigma antibonding 2pz molecular orbitals. Obtained from 2px and 2p5 orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and the negative lobes below the molecular plane. Such molecular orbitals are labeled as pi and pi antibonding. A pi bonding molecular orbital has larger electron density above and below the internuclear axis. The pi antibonding molecular orbital has a node between the nuclei. Now, the energy level diagram for molecular orbitals. We have seen that 1s atomic orbitals on the two atoms form two molecular orbitals designated as sigma 1s and sigma antibonding 1s. In the same manner, the 2s and 2p atomic orbitals, that is 8 atomic orbitals on the two atoms, give rise to the following 8 molecular orbitals. Figure shows you the contours and the energies of the bonding and antibonding molecular orbitals formed through the combination of 1s atomic orbital, and the figure B shows you the 2pz atomic orbitals and figure C shows the 2px atomic orbitals. Antibonding molecular orbitals sigma antibonding 2s, sigma antibonding 2pz, pi antibonding 2px and pi antibonding 2py bonding molecular orbitals sigma 2s, sigma 2pz, pi 2px and pi 2py. The energy levels of these molecular orbitals have been determined experimentally from spectroscopic data for homonuclear diatomic molecules of second row elements of the periodic table. The increasing order of energies of various molecular orbitals for oxygen and fluorine is given below. Sigma 1s, it is less than sigma antibonding 1s, which is further less than sigma 2s, it is less than sigma antibonding 2s and then sigma 2pz, and it is less than pi 2px, which is equals to pi 2py, but it is less than pi antibonding 2px equals to pi antibonding 2py, and it is less than sigma antibonding 2pz. However, this sequence of energy levels of the molecular orbital is not correct for the remaining molecules like lithium molecule, beryllium molecule, boron, carbon and nitrogen molecule. For instance, it has been observed experimentally that for molecules such as boron, carbon and nitrogen etc., the increasing order of energies of the various molecular orbitals is sigma 1s, energy is less than sigma antibonding 1s, it is less than sigma 2s, it is less than sigma antibonding 2s, which is further less than pi 2px, which is equals to pi 2py. It is less than sigma 2pz, further it is less than pi antibonding 2px equals to pi antibonding 2py, which is less than sigma antibonding 2pz. You have to learn this series to write the molecular electronic configurations. The important characteristic feature of this order is that the energy of sigma 2pz molecular orbital is higher than that of pi 2px and pi 2py molecular orbitals. Now, very important topic is the electronic configuration and the molecular behavior. The distribution of electrons among various molecular orbitals is called the electronic configuration of the molecule. From the electronic configuration of the molecule, it is possible to get important information about the molecule as discussed below. Stability of the molecules. If Nb is the number of electrons occupying bonding orbitals and Na the number of occupying the antibonding orbitals, then the molecule is stable if Nb is greater than Na. The molecule is unstable if Nb is less than Na. Now, the more the bonding orbitals are occupied, and so the bonding influence is stronger and a stable molecule results. And in second, the influence is stronger and therefore, the molecule is unstable. Now, a new concept, the bond order. Bond order is defined as 1/2 the difference between the number of the electrons present in the bonding and the antibonding orbitals. That is, bond order is equals to half Nb minus Na. The rules discussed above regarding the stability of the molecule can be restated in terms of the bond order as follows. A positive bond order, that is, number of electrons in the bonding orbital is greater than the number of electrons in the antibonding orbital, means a stable molecule. While a negative bond order, that is, Nb less than Na, means an unstable molecule. Or if it is 0, that is, Nb is equals to Na, the bond order means molecule does not exist. This is a frequently asked question, that why helium molecule or the neon molecule does not exist. So, you have to answer that the bond order of these noble gases is 0. The nature of the bond. Integral bond order values of 1, 2 or 3 correspond to single, double or triple bonds respectively as studied in the classical concept. Bond length. The bond order between the two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. That means, bond order and bond length are inversely related. Magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic. That is, all electrons are paired and it is repelled by the magnetic field. However, if one or more molecular orbitals are singly occupied, that is, unpaired electrons are there, it is paramagnetic, it is attracted by the magnetic field. For example, oxygen molecule. Bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic molecules. Hydrogen molecule. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in 1s orbital. Therefore, in all there are two electrons in hydrogen molecule, which are present in sigma 1s molecular orbital. So, the electronic configuration of hydrogen molecule is sigma 1s2. The bond order of H2 molecule can be calculated as given below. It comes out to be 1 by using the formula half Nb minus Na. The hydrogen atoms are together bonded by a single covalent bond. The bond dissociation energy of hydrogen molecule has been found to be 438 kilojoules per mole and the bond length equals to 74 picometer. Since no unpaired electron is present in hydrogen molecule, therefore, it is diamagnetic. The electronic configuration of helium atom is 1s2. Each helium atom contains 2 electrons. Therefore, in He2 molecule, there would be 4 electrons. These electrons will be accommodated in sigma 1s and sigma antibonding 1s molecular orbitals, leading to electronic configuration sigma 1s2, sigma antibonding 1s2. Bond order of helium molecule will be half 2 minus 2 equals to 0. Therefore, helium molecule is unstable and it does not exist. It is a frequently asked question. Similarly, it can be shown that beryllium molecule, the electronic configuration sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s2 also does not exist. That means when we will calculate the bond order, it will come out to be 0. Now, the third example, lithium molecule. The electronic configuration of lithium is 1s2, 2s1. There are 6 electrons in lithium molecule. The electronic configuration of Li2 molecule therefore is sigma 1s2, sigma antibonding 1s2, sigma 2s2. The above configuration is also written as Kk, the capital Kk, sigma 2s2, where capital Kk represents the closed K shell structure, sigma 1s2, sigma antibonding 1s2. From the electronic configuration of the lithium molecule, it is clear that there are 4 electrons present in the bonding molecular orbitals and 2 electrons are present in antibonding molecular orbitals. Its bond order is half 4 minus 2 equals to 1. It means that lithium molecule is stable because the value comes out to be positive, and since it has no unpaired electrons, it should be diamagnetic. Indeed, diamagnetic lithium molecules are known to exist in the vapor phase. The fourth example is the carbon molecule. The electronic configuration of carbon is 1s2, 2s2, 2p2. There are 12 electrons in carbon molecule. The electronic configuration of the carbon molecule therefore is, or the bond order of the carbon is half 8 minus 4 equals to 2, and the carbon molecule should be diamagnetic. The diamagnetic molecules have indeed been detected in the vapor phase. It is important to note that double bond in the C2 consists of both pi bonds because of the presence of 4 electrons in the 2 pi molecular orbitals. In most of the other molecules, a double bond is made up of a sigma bond and a pi bond. In similar fashion, the bonding in the nitrogen molecule can be discussed. Now, the oxygen molecule. The electronic configuration of the oxygen atom is 1s2, 2s2, 2p4. Each oxygen atom has 8 electrons. Hence, in oxygen molecule, there are 16 electrons. The electronic configuration of O2 molecule therefore is it is on the screen now. And from the electronic configuration of the O2 molecule, it is clear that the 10 electrons are present in bonding molecular orbitals and the 6 electrons are present in antibonding molecular orbitals. So, its bond order therefore is 2. So, in oxygen molecule, atoms are held by a double bond. Moreover, it may be noted that it contains 2 unpaired electrons in pi antibonding 2px and pi antibonding 2py molecular orbitals. Therefore, oxygen molecule should be paramagnetic, a prediction that corresponds to experimental observation. In this way, the theory successfully explains the paramagnetic nature of oxygen. Similarly, the electronic configuration of the other homonuclear diatomic molecules of the second row of the periodic table can be written. In the figure are given below the molecular orbital occupancy and molecular properties for boron molecule through neon molecule, though the sequence of the molecular orbitals and their electron repopulation are shown. The bond energy, bond length, bond order, magnetic properties and the valence electron configuration appear below the orbital diagrams. The diagrams are in front of you, from where you can predict and calculate the bond order, and you can predict about the bond length and the bond stability. Now, the molecular orbital occupancy and molecular properties for boron molecule and through the neon molecule. Now, let us discuss about the hydrogen bonding. Nitrogen, oxygen and fluorine are the highly electronegative elements. When they are attached to a hydrogen atom to form covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atom. This partially positively charged hydrogen atom forms a bond with the other more electronegative atom. This bond is known as hydrogen bond and is weaker than the covalent bond. For example, in hydrogen fluoride molecule, the hydrogen bond exists between the hydrogen atom of one molecule and the fluorine atom of another molecule, as is depicted below. From the figure now you can see that there is a hydrogen bond between the fluorine of the one HF and the hydrogen of the other hydrogen fluoride molecule. Here, hydrogen bond act as a bridge between the two atoms, which holds one atom by the covalent bond and the other by the hydrogen bond. The hydrogen bond is represented by a dotted line, while a solid line represents the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of the one molecule with the electronegative atom, fluorine, oxygen or nitrogen of the another molecule. The cause for the formation of hydrogen bonding. When hydrogen is bonded to a strongly electronegative element like X, the electron pair shared between the two atoms move far away from the hydrogen atom. As a result, the hydrogen atoms become highly electropositive with respect to the other atom X, which can be F, O or N. Since there is a displacement of electrons towards X, the hydrogen acquires fractional positive charge, that is delta plus, while X attain fractional negative charge, that is delta negative. This results in the formation of a polar molecule having electrostatic force of attraction, which can be represented as the dotted line between the two molecules. The magnitude of hydrogen bonding depends on the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. Thus, the hydrogen bonds have strong influence on the structure and the properties of the compounds. You will come across many questions which will be based on the hydrogen bonding. Now, let us discuss about the types of the hydrogen bond. There are two types of the hydrogen bonds. First one is intermolecular hydrogen bond. The second one is intramolecular hydrogen bond. Let's discuss each one by one. The intermolecular hydrogen bond. It is formed between the two different molecules of the same or different compounds. For example, hydrogen bond in case of HF molecule, alcohol or water molecules, etc., is intermolecular hydrogen bonding. You can see the structures on the screen. Intramolecular hydrogen bond. It is formed when hydrogen atom is in between the two highly electronegative, that is fluorine, oxygen and nitrogen atoms present within the same molecule. For example, in orthonitrophenol, it is an organic compound. The hydrogen is in between the two oxygen atoms. In the figure, you can see the hydrogen bond within the same molecule. Now, let me discuss about the conditions for the hydrogen bonding. The following conditions are necessary for the formation of hydrogen bond. The first one is high electronegativity of the atom bonded to hydrogen. The molecule should contain an atom of high electronegativity. Again, I am telling you, it is fluorine, oxygen or nitrogen bonded to hydrogen atom. The common examples are hydrogen fluoride, water and ammonia, that is NH3. The second important factor for the hydrogen bonding is the small size of the electronegative atom. The size of the electronegative atom should be quite small. This is due to the fact that smaller is the size of the electronegative atom, the greater will be its attraction for the bonded electron pair. This will cause greater polarity in the bond between H and electronegative atom, which results in stronger hydrogen bond. For example, ammonia shows hydrogen bonding while hydrogen chloride does not. Although both nitrogen and chlorine have the same electronegativity 3.0. Hydrogen bonds are not formed by Cl because of its bigger size than nitrogen. Now, let us discuss the difference between the hydrogen bond and the covalent bond. The hydrogen bond involves dipole-dipole attractions, whereas covalent bond involves sharing of electrons. Hydrogen bond is formed between the hydrogen atom and a highly electronegative atom F, O or N, whereas covalent bond is formed between any two electronegative atoms which may be of the same element or of different elements. The strength of the hydrogen bond is very small. Example, the bond strength of H and F bond is 41.83 kilojoules per mole. Whereas in the covalent bond, the bond strength of the covalent bond is sufficiently high. For example, bond strength of H bond H is 433 kilojoules per mole. Examples of the hydrogen bonded compounds. A few examples of compounds which exhibit hydrogen bonding are discussed below. Hydrogen fluoride in the solid state. Hydrogen fluoride consists of long zigzag chain of molecules associated together through the hydrogen bonds. Thus, hydrogen fluoride molecule is represented as HFN. In the liquid or the gaseous state, the chain however becomes linear. Water. Hydrogen bonding exists in water molecules also. In addition to two covalent OH bonds in the water, oxygen atom forms two hydrogen bonds. As a result of the hydrogen bonds, each oxygen is tetrahedrally surrounded by 4 hydrogen atoms, 2 by the covalent bonds and 2 by the hydrogen bond. In the figure, you can very clearly see the covalent bonds and the hydrogen bond. The associated water molecules may be expressed as H2O whole thrice N. Now, the next example is ammonia. Ammonia molecule has an electronegative nitrogen atom bonded to 3 hydrogen atoms. Due to the difference in the electronegativity between nitrogen and hydrogen, each hydrogen atom acquires positive charge. Thus, in the molecule, there are 1 negative site and 3 positive sites, so that the molecules of ammonia associates through hydrogen bonding to form long chain. Now, let me discuss the influence of the hydrogen bonding on the properties. Hydrogen bonding has important effects on many physical properties such as melting point, boiling point and the solubility of the compounds. The main characteristics of the compounds having hydrogen bonds are given below. association due to intermolecular hydrogen bonding. Two or more molecules of a compound exist as associated molecules. For example, carboxylic acids exist as dimers even in the vapor state. Higher melting and boiling points, the compounds containing hydrogen bonds have high melting and boiling points. It is due to the fact that because of the hydrogen bonding, the electrostatic force of attraction in the molecules become large. Consequently, larger energy is required to separate these molecules before they can melt or boil. The influence of the hydrogen bonding on the melting and the boiling points can be understood comparing the melting and the boiling point of the hydrides of the elements of group 14, 15, 16 and 17. Let us compare the melting and the boiling point of different molecules. First of all, the melting points. They are in Kelvin. Methane, it's 89.0 Kelvin, ammonia 195.5 Kelvin, water 273.0 Kelvin and hydrogen fluoride 180.7 Kelvin. From this data, you can see that the melting point of water is very high. It is just because the oxygen is highly electronegative and due to the intermolecular hydrogen bonding. Now, let us compare the boiling point of methane, ammonia, water and hydrogen fluoride. The boiling point of methane is 111.5 Kelvin, ammonia it is 239.6 Kelvin, water 373.0 Kelvin and hydrogen fluoride 292.4 Kelvin. The melting and the boiling points of the hydrides of the elements of these group are also plotted against their molecular masses. The melting and the boiling points increases as the molecular mass increases in group 14. This is mainly due to the fact that as the size of the elements of group 14 increases, the number of electrons also increases. As a result, van der Waals forces also increase and therefore, melting and the boiling points increase. However, hydrides of group 15, 16 and 17 do not show this trend. In these groups, the melting and the boiling points also increase with increasing molecular mass with the exception of first member. But the first member ammonia group 15, water group 16 and hydrogen fluoride group 17 have abnormally high melting and boiling points. The relatively high melting and the boiling point of the first member of each group is due to the intermolecular hydrogen bonding shown by these compounds. For example, the boiling point of hydrogen fluoride is much more than that of hydrogen chloride due to larger hydrogen bonding in the former. Similarly, we can account for the higher values of the boiling point of ammonia and water in their group. It is interesting to note that hydrogen bond in hydrogen fluoride is stronger than water. However, water boils at a higher temperature than hydrogen fluoride. This is due to the reason that each water molecule is bonded to 4 other water molecules through the hydrogen bonds. Now, you can see from the figure and you can compare the hydrogen bonding in hydrogen fluoride and water. Whereas, each HF molecule is bonded to 2 other HF molecules through hydrogen bonds. Now, the influence on the physical state. Hydrogen bonding also influences the physical state of the substance, solid, liquid or gas. For example, both oxygen and sulfur being from the same group, but water is a liquid at ordinary temperature while H2S is a gas. This is explained on the basis of electronegativity values. Water molecules and H2S molecules, the electronegativity of oxygen is 3.5, whereas electronegativity of sulfur is 2.5. The electronegativity of hydrogen is 2.1. In water, oxygen is highly electronegative, so that it forms hydrogen bonds. As a result, the molecules of water get associated with one another and this raises the boiling point of the water. Consequently, water exists as liquid at room temperature. On the other hand, the electronegativity difference of the atoms in the H2S is less and hydrogen bonding in H2S is almost negligible. As a result, H2S is not associated and exists as a gas at room temperature. The next impact of the hydrogen bonding is on the solubility. Hydrogen bonding also influences the solubility of one substance in another. For example, alcohol is highly soluble in water due to hydrogen bonding with the water molecules. Volatility. The compounds involving hydrogen bonds between different molecules such as ammonia, water and hydrogen fluoride have higher boiling points. Therefore, they are less volatile as compared to the other corresponding members of their groups. The enthalpies of vaporization follows almost the same pattern as shown by their melting points and the boiling points. For example, in group 17, the enthalpies of vaporization decreases in the order. HCl has lesser than HBr, HBr has lesser enthalpy of vaporization than HI and which has lesser enthalpy of vaporization than hydrogen fluoride. Similarly, in group 15 and 16, the trends are H2S less than H2Se, less than H2Te, less than H2O, and in the 15th group, PH3 less than ASH3, which is less than SBH3 and which is further less than ammonia, that is NH3. So, let us summarize what we have studied today. The molecular bonding theory describes the bonding in terms of the combination and the arrangement of the atomic orbitals to form molecular orbitals that are associated with the molecule as a whole. The number of the molecular orbitals are always equal to the number of the atomic orbitals from which they are formed. Bonding molecular orbitals increase electron density between the nuclei and lower in energy than the individual atomic orbitals. Antibonding molecular orbitals have region of zero electron density between the nuclei and have more energy than the individual atomic orbitals. The electronic configuration of the molecules is written by filling the electrons in the molecular orbitals in the order of increasing energy levels. As in the case of the atoms, the Pauli exclusion principle and Hund's rule are applicable for the filling of the molecular orbitals. The molecules are said to be stable if the number of the electrons in the bonding molecular orbital is greater than in the antibonding molecular orbitals. Hydrogen bond is formed when a hydrogen atom finds itself between the two highly electronegative atoms such as fluorine, oxygen and nitrogen. It may be intermolecular, that is existing between the two or the more molecules of the same or the different substances, or intramolecular, that is present within the same molecular. Hydrogen bonds have a powerful effect on the structure and the properties of many compounds. So, dear students, today we have studied about the molecular orbitals, the bonding and the antibonding orbitals, then how to calculate the bond order and the stability of the molecule and the types of the hydrogen bonding and its impact on the various physical aspects of a compound. I hope everything is clear to you. Thank you.